我们讲到这个如何去看 Admittance. So we'll finish with the transformation of impedance to admittance. So let me give you one example. On Smith chart, 在 Smith chart 上头 if you have a load that is 2 minus GA multiplied with 1, 那你如何在这个地方算它的 input impedance， 然后呢把这个 input impedance 的值这个换成 admittance， 然后在 Smith chart 上头读出来。Okay, so this is the purpose for this example. So first, we identify this point. Okay, on Smith chart, the RL is equal to 2 and XL is equal to -1. So we look for this point on the Smith chart. And it turn out that the point is right here. Okay, if you just check the value for the RL right here is equal to 2. Okay, 在这个圆上头 for the load. And if you check the value following this line to this point is equal to -1. So this point corresponds to the low impedance 2 minus GA. Okay, but we are asking for the input impedance at this point, that is 0.1 wavelength from the load or toward the generator. Okay, so we have to move this line by 0.1 wavelength toward the generator. So that is a clockwise direction. So let's try to move this line over. But given the transmission line, 你如果有一个 transmission line 的话，它就有一个 SWR circle， 它的所有的值都是在这个 SWR circle 上头。So you better to draw this SWR circle first. Okay, 先把它画出来。For given transmission line, you must have a SWR circle. Okay, so when we move this line toward the generator by 0.1 wavelength, we are looking for the intercepting point of the line on this SWR circle. 每一个 transmission line 都有一个 SWR circle, 因为它的 gamma 的绝对值是固定的。Okay, so let's try to move this line by 0.1 wavelength. Then you intercept your line with this circle at this point B. And you can come to just read the value for B to determine the input impedance at this point. 所以很清楚，很简单，有没有 ？Okay, so let's try to read it. Well, this circle is going to give you the value for RL. So this value is somewhere here. I cannot read it because it's too small. Okay, 在这个地方可能是0.6的地方。Okay, so you have RL equal to 0.6, and for the XL, is intercepting this line, so this value is going to give you perhaps the 0.6 minus 0.6, 0.6减掉0.66 GA 的地方，就是这个 input impedance. Okay. But the purpose for this example is to find out the admittance looking into this line at this point. And I told you last week that you can just move this line by quarter wavelength to find out the admittance, right? So it's easy that you just extend this line by over this direction and then rotate this line by 180 degrees. 1/4波长是相当于你在这个图上头呢转180度。Okay, so if you want to read the admittance, you read the value at this point. 把它给拉到这里来，然后呢看这个焦点的地方。Okay, so it's easy enough, right? That's quarter wavelength toward the load, toward the generator. So the value you read this circle correspond to admittance equal to 0.72, and then this line, the value is going to give you 0.82 J, and this is the admittance correspond to the value that you look into this line from this point. 所以一个简单的结论的话，就是你如果要去找出这个 transmission line 哪一点你要看过去的 admittance 的话，你就先找出它的 impedance, and then flip the line by 180 degrees to find the intercepting point, and then again you read RL and XL to give you the admittance of the line. Okay, very simple rule. 有没有问题？非常简单 ，right？ 那重要的是这个在这个式子上头呢，有4/4波长的这个移动，给你 admittance 类似的一个式子可以让你用。Okay, there's a reason to deal with the admittance because very often that you want to have impedance matching for transmission line. So let me give you one example. Okay, usually if you put some arbitrary load onto transmission line, there will be reflection of power, and that is something you don't want because the energy efficiency is going to be reduced if you have reflection from this transmission line. Sometimes it's not so easy to connect a serial resistance or impedance to the line to make the energy not reflected back. Okay, so occasionally you're going to connect a parallel line to this transmission line, and for parallel circuit, you know that it's easier to deal with admittance, not quite resistance. 如果说是串接的话呢，你加这个impedance 比较容易，但是呢，如果是并接的话呢，你加 admittance 比较容易 ，right? So suppose that there's some reflection of energy from this load, and you want to connect a parallel line to this transmission line such that you don't get reflection from this transmission line. So you want to do impedance matching. 做一个这个impedance matching 的动作 ，OK. So let's pick up a point here with a distance of d from the load, and then just connect it with the parallel transmission line. So there are two transmission lines in this configuration, OK. 两个 transmission line， 你预期会有两个SWR circle 在 Smith chart 上头了 ，OK. But the purpose is that you pick up a point. Okay, and then connect a transmission line with some impedance looking into, or with some admittance looking into this direction. And you want the signal coming to this point and suffer no reflection from this point. So the impedance or admittance at this point has to be the same as the characteristic impedance or characteristic admittance. OK， 基本上你在这里接了一条线之后呢，这里看进去的这个 impedance 或 admittance 已经改变了。那你要把它变成就是跟你进去的 characteristic impedance 或者是 admittance 一模一样。这时候呢，你不会有反射 ，because your reflection coefficient is equal to what? Z input, Z characteristic impedance, or this is also equal to what? Y input, Y0, Y input plus Y0. So if you have this equal to 0 or this equal to 0, then the whole thing is going to be 0. You don't have reflection. Okay, so well, the easiest way to have a short circuit or open circuit. 所以呢，这一端这里呢，你可以用最简单的方式。Last time I showed you a video, right? It's very easy to disconnect the end of the transmission line and make it open circuit, or it's very easy to connect it back to make it a short circuit. So for this point, you can set it up as an open circuit or short circuit. 你看，一个简单的就是把这个线呢连在一块，或者把它打开。And this is called the shunt stub. Okay, 一个 shunt stub to connect it to your transmission line and make this transmission line no reflection. 那它的这个简化之后的一个 circuit diagram 就是这么一个 circuit diagram, very simple and easy. You have a parallel impedance right here, or parallel admittance. So the total admittance now is equal to ys plus yd. Okay, 在这个地方从这里看进来。And of course, you have to determine the length of the transmission line you want to connect your shunt stub. And you also have to determine the length of this shunt stub. 所以这里有几个参数 ，D 你必须知道 ，L 你必须知道。OK， 那这是你的天线，譬如说 ，so this is known to you already. OK， 有没有问题？很清楚的这个解释 ，right？ 好 ，now you want to do impedance matching, so basically if you add these two together, ys plus yd, that is your input admittance. Now, if this input admittance is equal to the characteristic admittance, then you don't have reflection. So the design rule, the design criterion is that you want to have your input admittance equal to the characteristic admittance. 有没有问题？赖博玉，有没有问题？听得懂吗？听得懂来？好，所以这个设计上头的话，基本上就是要连一条这个short circuit transmission line 或者是 open circuit transmission line 在某个地方，然后让这个 input impedance 看进去呢，就等于你的 characteristic impedance. That's it. Okay, but for this kind of parallel connection, it's easier to deal with admittance than dealing with impedance, because you just sum the admittance together for parallel circuit to get the total admittance. Okay. 所以我们来看一个看它这个 in general how do we do impedance matching? Okay. Now assume your characteristic impedance is y0. Okay. For short circuit or open circuit, you can pick up the formula I told you 2 weeks ago, and then just calculate the impedance for short circuit transmission line. Well, you can do the same thing for open circuit transmission line. It turns out that the short circuit impedance for transmission line with the length of L is purely imaginary, right? 如果还记得的话，我们在前面有讲过。在哪里啊 ？Impedance transformation. Okay, right here. You have a open circuit termination, and this is your impedance for open circuit transmission line, and it's purely imaginary, right? For the same thing, you calculate the impedance for a short circuit, and it's also pure imaginary. 所以对一个 short circuit transmission line 或者 open circuit transmission line 来讲的话 ，your input impedance is pure imaginary. OK， 它是纯虚数。So 所以你可以预期它是一个纯虚数的话呢 ，you can start to simplify your thinking a little bit. Okay, so ys is also pure imaginary because ys is just the inverse of your short circuit impedance， 把这个导过来，它还是一个纯虚数。OK， 所以呢，我们可以整理出3个步骤来做 impedance matching， 但是呢，这是个重要的一个特性，你要注意到。OK，the first step to do impedance matching is that you first find a length of D. Okay. Once you find a length of D, then you do a admittance transformation up to this point to get a value of the input impedance without this line. That is Y0 characteristic impedance minus YS. OK， 你设法找到一个 D， 让你的这个 input admittance equal to this value. Okay, well, we can always find out this value because we can walk on the transmission line SWR circle, try to find out this value. The purpose to have this value is that because later on, once you put this line into the place, then the total input admittance now is equal to this YD plus YS. So you can cancel out this YS, right? 然后呢，你找一条这个线，把它这个做短路 ，then you have a short circuit admittance, and then you add these two terms together, Y0 减的 YS 再加上 YS， 当然你就得到 Y0， right？ 最后一个动作，你把这2个 admittance 加在一块 ，OK。Once you add them together, because this is minus YS. This is YS, so you cancel out. Your input admittance now is equal to Y0, the characteristic impedance. OK， 所以有3个步骤，你可以做到这个 input impedance 的这个impedance matching。了解吗？最重要的就是把这2个加起来等于这个 Y0. That's it. OK, but you have to determine D and L. These two variables have to be determined from your Smith chart. Okay, let's look into this a little bit carefully. What we are dealing with is a Smith chart. And all the values on the Smith chart are normalized to the characteristic impedance or characteristic admittance. 所以在 Smith chart 上头呢，所谓的 Y0 减到 YS 的话，基本上是你要把这个 Y0 提出来。Okay, you have to pull out this Y, capital Y0. And then you look for the value of 1 minus small ys. This 1 is very important because 1 tells you that this is the normalized characteristic impedance or normalized characteristic admittance. Right? 你如果把 Y0 normalized to Y0 is going to give you 1, or you have Y0 normalized to Z0, you have 1. Therefore, you're looking for a circle that corresponds to 1, RL equal to 1, or the normalized admittance equal to 1. Okay, well, same thing on the Smith chart. You want to use the Smith chart to design a section of short circuit transmission line with impedance equal to small ys. Okay, you have to normalize this to the characteristic admittance. Okay, so let me give you one example. 我给你一个例子，然后呢 we walk down these steps 1, 2, 3 to figure out D and L. 所以在这个问题里头呢，你要的这个变数是你要知道的这个变数是 D 跟 L as a function of wavelength. OK， 你拿一个 transmission line 过来的时候呢，你必须决定它长度。OK， 这个长度多少？我们现在用 Smith chart 来决定。OK， so let's pick up one example. Suppose that you have a transmission line with some row impedance that is equal to 25 minus J50 ohm. and the characteristic impedance for this line is 50 ohm. Okay, and definitely you have reflection because you can calculate this. Just put this as a low impedance, 25 minus J 50 into this location, and Z naught equal to 50 ohm. Then you have non-zero reflection, and you want to solve this problem. 你不希望它有反射，但是呢，你现在这条线呢把这个值放进来之后，你有反射。Well, the solution is that you find a shunt stop. You design a shunt stop right here with a short circuit. But of course, you can put the open circuit here, all right? 你可以在这里放一个 open circuit 或 short circuit. That is okay. And then you want to determine D and L as a function of wavelength. Therefore, you don't get reflection from this point and back. 所以这个问题的设计是这个样子。有问题？陈立昂，告诉我一下，我们现在做这个问题是目的是什么 ？Good， 陈立昂有在听讲，这个线上你不需要有反射，那要怎么做？
就是决定一个离漏的一段距离，或者上面并联另外一个 transmission line。
很帅哦。然后呢，我们要在上头决定哪两个参数。
D 跟 L。
你怎么没有睡着？这么好，这让我愿意继续讲下去了。Good. Okay. Now, for this transmission line, there's a SWR circle. Right? For this transmission line, there's another SWR circle. Let's first normalize this to characteristic impedance, and then find out the input impedance from this point. Okay. So the first step is that we convert this low impedance into a normalized value, 0.5 minus 1Ga, and try to locate this point on this Smith chart. And for 0.5, it corresponds to this circle right here. And you read this value 0.5, and for this point A. And for this point A, the XL, the reactive part, is equal to 1 right here. So you identify this point as A, as the low impedance, okay? 然后呢，你要找到它的这个 low admittance. Just flip this point 180 degrees to this point. Okay, so you can read the low admittance at this location. 所以你找到它的这个 YL, normalized YL at this point. Okay. And then let's go back to the first step. Okay. The first step is that you want to find D so that the real part of your low admittance is equal to 1. 来，在这个地方，这是第一步，你要找到它的 D, and then the input admittance at that point has a admittance equal to 1. Okay, the real part of it. So let's come down. Okay, so once we find the admittance at point B, 这个地方对应过来，这里是 0.4， 并不是1。所以呢，我们必须在这上头动，动到呢这个 0.4 呢变成1， 1在哪里？1在这里，这个圈圈。This circle give you value of 1。所以呢，你要移动这一点，移到这里来，哎，碰到这里了，或者是呢继续往下移到这里来，碰到这一点。 这两点都可以用 ，because this is a circle of 1. Okay, so this point is right here. This point is right here. Give you an admittance of 0.4 plus 这个是 0.4 plus this value is I think is 0.8 正的 0.8j. But at this moment we don't care about the imaginary part yet. 我们不在乎它的虚数部分，我们在乎它的实数部分。这里呢必须变成1。Okay, and the circle of 1 is right here. So you have to move B. You have to move B to this point or this point. Because the circle of 1 is this light blue circle. Okay. 所以呢，往这边移，往这里动。You can move 0.063 wavelengths to this point to change the value of 0.5 of your admittance, the real part of admittance, to what? Okay. And once you move this B to this point, you have 1 plus 1.58j. Another thing is that another solution is that you can move this point all the way down to this point. Then you're going to get 1 minus 1.58j. Up to you. 你可以决定你要移这么多，决定这个D 是 0.063 wavelengths, or just move all the way to this point. 那在设计上头的话，你当然是觉得 well 移得越少越好嘛 ，right? So you just move this point to this location with D equal to 0.063 wavelengths. That's it. And then you end up having this result at this point. 有没有问题？清楚？有没有？第一个步骤就是把这个 0.5 换成1。OK， 这就是第一个步骤。为什么换成1？因为之后呢，我还要把这个拿掉。所以呢，这里 normalize 之后呢，这里变成1减1会等于0。OK， 之后我还要把这个消掉。Okay, how do I do it? Well, now I move to this point, C, so I have this result. And then I want to determine the length of L, the second parameter L, so that the y-axis looking into this shunt stub give you minus 1.58j. 我如果要把这个消掉的话呢，我必须 create a y-axis equal to minus 1.58j. Right? 好。Now we are dealing with the second transmission line. This SWR circle is associated with this transmission line. Now I need to identify the SWR circle for this line. 这是第二条线哦，它有第二个 SWR circle。OK， 我们当初在决定这个 SWR circle 的时候呢 ，we calculate the low impedance to determine this point, and then draw a circle on it. The same thing, you look into the short circuit at this point. Your RL is equal to 0. For open circuit, your RL is infinite. It's this point. And for short circuit, your RL is this circle. 你如果注意看的话，这里从多少 1.2 and then no 这个是这个越来越小，这里是 RL 越来越大到 open circuit. Okay, if you walk in the other direction, the value is dropping all the way to 0. Okay, so this means that your SWR circle for short circuit is the outermost line on this Smith chart. 你如果沿着它最外缘画一个圆下来的话 ，is your short circuit transmission line, SWR circle. This one. Okay, because this point is the short circuit point. Your RL drop to 0 at this point. Okay, so for this transmission line, you identify the SWR circle like this. And then you want to design this line with the length of L so that your input admittance is equal to minus 1.58 J. 这一点是我的 short circuit 的resistance RL equal to 0， 所以 short circuit 的 admittance 在哪里？180度在这里。所以呢，我移下来，移多少呢？我可以找到一个负 1.58 J 的这个 admittance。Well, you come and look, continue to look. You find that this point is somewhere here. If you read this number, 读到这里来的时候呢 you find that this is 1.58, but it's below this line, so it's negative value, minus 1.58 J 在底下。OK， 其实 1.58 的话，你已经知道了，这个点，这里是C 这个点，这里上来是 1.58， D 这个点呢，从这里下来是负 1.58。So you know that if you move your if you select the length of your line all the way down to this point, then you have minus 1.58 J 在这个地方。OK， 你必须从这里移动多少距离呢 ？Well, just read the length from this Smith chart. You have to move 0.09 wavelength. OK， 所以刚刚那个同学告诉我们，我们要决定 D and L. We have the answer. D is equal to 0.063 wavelength. L is equal to 0.09 wavelength. OK， 所以你的最后的 Y, your input admittance from this point is equal to 1 plus 1.58 J plus minus 1.58 J. You end up having 1. Okay, and then you achieve 1 minus 1 equal to 0. You don't have the reflection. Okay, let me give you a review. Well, the purpose for this problem is to design a D and L so that you don't have any reflection of signal from this point back. Okay, the first step is that you normalize this low admittance, and then find out that in fact you have some value in front right here. B is so there's some real part of it, okay, and then you want to determine D, so you move this B on the SWR circle to find the point where the real part of the input admittance is equal to 1. And then whatever you have for the imaginary part, you design a length of this shunt stub to cancel out this. So this is the design rule step 1, 2, 3. OK， 所以这3个步骤你留意一下，回去复习一下。那基本上呢，就是要最后从这里看进来呢，你的 input admittance has to be equal to 1. That is equal to your characteristic admittance. Okay, therefore, when you calculate the reflection coefficient, you cancel out the numerator. Therefore, you don't have any reflection. 有问题？没问题 ，right？ 所以这是在 Smith chart 上头把这个 impedance 换成 admittance 的好处。你可以做一个并联的电路，然后呢，直接用相加的动作，把这个最后的 total input admittance 呢，把它加起来。OK， 我们的 transmission line 就上到这里为止。然后呢，再下来 ，we're going to talk about electric field, magnetic field. But when we deal with field, the concept is a little bit more complicated because a field is derived from a force, and a force has a direction and has a magnitude. This means that we have to deal with vectors. Okay, now when we deal with the voltage and current, it's nothing to do with directions, so we can just use the scalar. 这些都是 scalar. Okay, but when we start to talk about field, again, the field is derived from a force, and force is a vector. So we have to review a little bit the vector calculus, but we're not going to spend a lot of time on vector calculus. Okay, presumably you have learned about it, I think, in the first year or second year. I think your second year of your education in the university, you learn about vector calculus, 或者是从工程数学里头学到的 right? So we'll just spend a little bit time to review vector calculus, and then move into electric field and magnetic field. 这应该是那个 D.K. Chen 那本书的第2章。Okay, I put it into chapter 3 for my handout. So we'll review some vector calculus. Well, unlike a scalar, you have two important characteristics for a vector. For scalar, basically, it just tells you the magnitude of something. For example, voltage, 5 volt, minus 3 volt, and so on. So you have plus minus magnitude of some physical quantity. 那它完全是一个数值。But for vector, you have magnitude and direction, because when we deal with force, there's a direction and magnitude associated with it. Okay. So we have to understand both the direction and magnitude for a physical quantity like field, like electric field, magnetic field. And let me quickly show you a 5-minute tutorial for the basic concept of a vector. And this is again from YouTube, and it's very brief and very simple. I just want to sort of wake you up and sort of start the concept of the vector. I'll 让你开始能够了解。Well, this tutorial is going to be very, very simple.
A quantity that has both magnitude and direction is a vector represented by an arrow. The arrow's direction is the direction of the quantity, and the length of the arrow indicates its magnitude.
应该把这灯关掉一下。
Displacement, velocity, and acceleration are all vectors. In equations, vectors are written in boldface. Ordinary quantities such as time and mass are scalars. In equations, scalars are written in italics. The magnitude of a vector is also a scalar, the same letter, but in italics. With vectors, even the most familiar mathematical operations acquire an entirely new meaning. For example, when two vectors are added together, the sum isn't merely a number, it's a new vector. Also, vectors can be subtracted from each other, and the result is another new vector. A vector can be multiplied by a scalar. This new vector has the same direction if the scalar is positive, but its magnitude can be different. Multiplying a vector by a negative scalar reverses its direction. A vector can be multiplied by another vector. The dot product of A and B is a scalar that measures the tendency of the two vectors to point in the same direction. A dot B is equal to the length of A times the length of B times the cosine of the angle between them. If A and B are perpendicular, their dot product is 0. And the dot product of a vector with itself is just the square of its length. The cross product of two vectors is a new vector, perpendicular to the plane of the two original vectors. Its length is the area of the parallelogram formed by the original vectors. Its direction is determined by the right-hand rule. The cross product measures the tendency of two vectors to be perpendicular, and it's one of the more effective tools for describing, spinning, or rotating objects. Vector algebra makes use of two perpendicular unit vectors, I and j. The little hat over the vector means that it has length 1. The vector from the origin to the point with coordinates x, y is the sum of two perpendicular vectors, a horizontal vector xi and a vertical vector yj. With the help of I and j, adding and multiplying vectors can be accomplished by ordinary algebra. In three-dimensional space, a third unit vector k is used. K is perpendicular to the plane of I and j. A three-dimensional vector is written xi plus yj plus zk.
OK， 所以这个是这个 vector 的一些基本概念。我想这个大概让你们想起以前高中的时候学的一些东西 ，right？ 在物理上头，在电磁学里头呢 ，we have two important concepts. Okay, one is that flux. And flux is that you integrate the vector over some surface, and we call this flux. Okay, so if you have a surface integration of the vector on surface, then we call it flux. But sometimes the important physical quantity is associated with the integration of the vector along some line 在某一条线上，而不是一个面上。Okay, 尤其是 when we deal with the magnetic field, then we very often that we deal with the line integration of the vector of the magnetic field along some path to determine the current related to the magnetic field. So there's another important concept, that is the circulation. Circulation, it means that you do a cross-path integration of some vector along some line, and this line is sort of cross path, and it tells you how strong this physical quantity can circulate along some path. And this is closely related to the magnetic field we're going to study. Okay, so when you deal with the vector, when we review the very basic vector calculus, you always have to come back to think about the physical reason that we want to study this. Because we are not teaching mathematics, 我们不是在教你数学 ，alright？ 那在这个电机系里头呢，我们要教你怎么用。那这个数学怎么用到这个物理上头的话，你要在学数学的时候，随时想一下这个重要的这个计算是什么。And one is flux, and one is circulation. And flux is the surface integration of some vector, and circulation is the line integration of some vector over some cross path. OK， 所以这两个概念的话，你应该先记住，然后呢，我们继续往下学数学。OK， flux and circulation. So in the video you just saw the representation of a vector is quite simple, but there are two important ingredients. One is the magnitude and one is the direction. Okay, if we put a small hat on this vector, then it's a unit vector with the length of 1. And then you give this vector magnitude called A. So the total length of this vector is capital A, and the direction is pointed to some direction represented by this unit vector. So a vector has a magnitude of A, capital A, pointing to some direction denoted by this small a with a hat right here. And this small a with a hat is called unit vector. Okay, that has a length of 1. So this is the simplest, the typical representation of a vector in space. Well, when you deal with the sum of a vector, you need to deal with the magnitude together with the direction. Okay, and you can do a head-to-tail construction of the vector to get the sum of two vectors. And this was also given in the video, right? And this is a summation. Well, it can be a subtraction because this magnitude could be negative. And if we flip the direction of the vector, then this magnitude becomes negative. So this represents a plus b or a minus b, depending on the question you will be dealing with. And for the multiplication for vector, there are two kinds of multiplications. The first one is called scalar product. And in the video, it already tells you that the scalar product or dot product tells you how good these two vectors are aligned along the same direction. 基本上呢是the multiplication of A with the projection of B along A. So if you project a lot of B onto the direction of A, then you get a large magnitude. 它告诉你说这个计算告诉你说这两个 vector 呢有多么的平行。Because this cosine theta AB, if this theta AB is equal to 0, then the multiplication of this is going to give you the maximum value. Okay, 所以这个 vector dot product 呢，给你一个这个 感觉就是这两个 vector 有多么平行。But the result is a scalar, it's no longer a vector. 两个 vector 的 dot product 给你一个这个scalar， 不再是一个 vector。OK， 我们休息个10分钟，然后等下再继续。